Hi everyone, and today I'm very excited to present to you my latest research of using large language models as a system in order to solve this abstraction and reasoning corpus challenge. Right? So the thing about this ARC challenge is that it has very, very difficult patterns, all right? Because if you look at this thing here, you have inputs to outputs like that. You don't know what the rule is. Okay, it could be in this case, the rule is fill in the yellow squares, all right? There could be other cases where the rule is like shift the square to the left, expand the shape, and so on. So you don't really know what exactly this input-output relation is. Okay, and you need to infer this input-output relation from your example test cases, or sorry, your example training cases, and map it to the test case over here. So this is a difficult problem for programs because it is something that, you have to do something that you have not programmed beforehand. And you have to be very versatile. And currently, the state of the art for this is about 30.5% on the hidden test set, okay, which is not that great, but it also highlights the difficulty of this challenge. So in this work, I did on the easier training set, and I got about 45% out of 111 problems. I solved about 45%. So that's one of the first steps towards solving intelligence, I believe. Okay, but in the grand scheme of things, actually, I think the ARC challenge is not enough for intelligence, right? I believe that the true test of intelligence will involve interaction with other agents in a more dynamic environment. So the ARC environment is a little too static for my liking, but we can use this to try to solve the grand problem of intelligence. So this can be a first stepping stone. So what are the methods usually used to solve the ARC challenge? Okay, or what are the methods commonly used in the field right now for AI? So the first kind of method is the program synthesis method, or GoFi. They call it good old-fashioned AI. Yeah, I will offend a few people by saying this word GoFi because this refers to rules-based AI. Like, for example, you construct a knowledge graph, construct a decision tree, do some rules in order to determine whether or not like to do a particular action. Yeah, so last time there's this thing called expert systems. Okay, I mean now there still is, where you encode all the expert knowledge into a structure, and then you can use this structure to determine what to output. So this expert knowledge system, it works pretty well. I mean, it's reliable for quite a lot of domains, but it requires a lot of hand tuning. All right, so there came the deep learning era where we say that, okay, we can just use data. Okay, just feed the data into the model, and the model can learn arbitrary relations. It can learn arbitrary features, like, for example, a convolutional neural network. It's said to learn features in the filters so that you can use these features for other tasks. Okay, but there's a problem with that as well. This kind of methods use a lot of data. If you don't have the right data, you may not generalize very well. Okay, so these two methods try to solve a similar problem, but they each have their own drawbacks. Okay, but unfortunately for ARC, none of this work. Okay, because the first method, program synthesis, you have too many rules that you need to program in. Just look at this case here. There's so many. This is just one rule called fill in the square that's enclosed by the shape. There could be other rules like fill in the boundary, fill in the left side, fill in the right side. It's almost impossible to predict, okay, what kind of pattern it would be, or what kind of rules there would be, because if you just combine a few rules together, there's quite a lot of combinations. Okay, I mean, if you have 100 rules for the first one, you apply 2 rules in succession, that's 10,000 rules. And if each rule can take in a parameter that, you understand what I mean, right? You have a lot of rules that you need to program in for this, and that's not very feasible. Deep learning, you only have 3 samples for the ARC test. 1, 2, 3, 2 or 3 samples. That's not enough to learn. So how can we actually learn it fast? So there's this new technology, okay, not say new, but already 5 years old, but made popular this year by ChatGPT. And this is called the transformer. So why transformers? All right. Transformers actually use this new method, okay, called the self-attention, where you feed in this. Let me just draw here. There's a way to update the context of what you have. Okay, let's say if you have like write the text in Shakespeare style, and then you type in your text here. Okay, while traditional models will require you to keep giving in more and more input data, okay, in order to form the Shakespeare kind of knowledge. Yeah. In this case, because transformers can use like unsupervised learning of next token prediction on arbitrary documents online. Okay, it's able to learn all these arbitrary relations that are not task specific already. And this is the beauty of self-attention, right? So you see, if let's say at training time or at test time, I want to change how this text is output. Okay, what I do is, in order to influence this text, I have to use some form of attention to my context. And how do I attend to this context? You have this query, which is like maybe your current token, a query, like, and your key and your values will be everything else of this whole context fed in here. So in some sense, you can pay attention to what has come before in that context. And this allows the transformer to be flexibly prompted to do various tasks. Okay, I mean, how many of you here have tried this before? Like, you just give it a task description in words, and the transformer or ChatGPT is able to come up with something reasonable. Okay, have you tried this before? You say like, write in this style, write in that style, or like, you are now a calculator, you are now a financial assistant. Yeah, how many of you here have tried that and it worked out for you? I mean, maybe you can just give me a show of hands or something.
Yes, I mean, there's a lot of generative capacity, right?
Yes, correct. So this kind of goes against the intuition that we have, right? That like deep learning, you need a lot of samples. But transformers, it seems that because of this unsupervised training and with the self-attention that we have over here, it seems that the transformer is able to be flexibly prompted in a very short amount of time. You just need to give that context. And if the context is something that is similar to what has been seen in the training data, you might already be able to replicate that style or do that task without even further training, right? So that's quite interesting. So transformers, you can do zero-shot prompting, which you can just say you are sentiment analysis tool. Okay, does sentiment analysis very well, because a lot of corpus are sentiment analysis corpus, like positive or negative movie reviews. It can also be few-shot prompted, to a limited extent. Okay, like for example, you can give like, if you want it to generate in a style of an artist or style of a writer A, the writer A is not in the training corpus, but you can give some styles of like this writer. Like for example, if the writer is like talking Singlish, like I want this lah, you can give that example, like don't do this. I mean, for example, if you have this, okay, Singlish is in the training corpus, so you don't have to do this if you want it to output Singlish. But I'm giving you an example. If let's say it's not in the training set, okay, you can actually still few-shot prompt the transformer to generate something reasonable. Okay. Transformers also, because of the way it attends to the context before it, it can be prompted sequentially. So stuff like let's think step by step, okay, prompts the large language model to kind of break down the problem into step 1, step 2, step 3. Like it enables it to solve some word math problems in this way. Okay, but it's not perfect. But the idea is that because of what you generate first, okay, like for example, in my evolution game, okay, what I did was I asked it to generate the species, okay, then generate the habitat. After that, I asked it to generate the abilities, or I mean, we can call it traits. Okay, so by doing it in this way, when we actually generate the species, like for example, frog, we know the habitat will be pond because it can refer to earlier. Then the traits can be like jump, like amphibious, and so on, because we already know what habitat and what species is. Okay, if we had reversed the roles, okay, we do the traits first, then the species, then the habitat, it will not be as accurate. So broad to specific prompting is something that is very, very important. Okay, I like to emphasize this. I think a lot of papers focus too much on let's think step by step. I mean, DeepMind tried to improve it. Have you read the DeepMind paper on this? The prompter paper? You know what's the improved prompt for this? Anyone? Okay, so I mean, in their paper, they say that this works better for math problems. Take a deep breath, and then let's think step by step. So it's, I mean, that's I guess trying to navigate the space of possible programs, like using context prompting. But that's not the best way, right? The best way is still using broad to specific prompting. If you already know what things to, if you already know what things to output, you should output the first category, then the second category, third category, and so on. So yeah, that's it. All right, transformers can also facilitate very specific generation, okay, especially if you have stuff like this, retrieval augmented generation. Okay, you have memory or relevant context. You can retrieve from a corpus of documents and so on. You can use these documents to sort of prompt your large language model, okay, and then you can get it to generate stuff that are more specific. Okay, this is especially the case when you want to like reference like some historical facts, you know. If you were to just use the large language model itself, it might hallucinate, you know, generate the wrong stuff. But once conditioned on all this, it will generate better stuff. Okay, so there's another way to improve the performance is to use tools. So tools, something like if you are using like image tools, you have Visual ChatGPT. If you are using like stuff like functions, OpenAI functions, you can imbue external functions like calculator, search the date and time, search the web, and so on. So these are stuff that you can use to, augment the what you need to generate, okay? Because the large language model is just about probability of tokens, okay? It doesn't really do math very well, okay? Trust me on that, okay? It doesn't do math very well. I tried it, okay? Yeah, I see a lot of functions on the, see a lot of chat. So Volodymyr, you said that external functions are amazing. Okay, we are integrating with third-party services. Yeah, this is very useful for business use cases as well. Okay, because the large language model can only do so much. The rest, if you want reliability, you want some form of specificity, you might need some external tools. So what does all this mean for ARC? Okay, in ARC, if we just use the GPT to program from input to output directly, it's bound to fail. Okay, because ARC requires very specific kind of programs. All right. It also requires some form of context as to what the large language model is supposed to generate. You cannot just prompt it straight away. Okay, but before I go on to the approach that I tried, okay, let me just share with you what transformers are not good at. Okay, so that you can use this, like if you want to do your business use case or whatever, you can use this as well. Transformers don't follow rules very well. Okay, so what happens is that when we want transformers to like say, if you see the word David, okay, reply yes, you know, that kind of thing. Yeah, it works most of the time, but sometimes, you know, if your context length is very, very long, maybe the word David appears in a very, very, in like somewhere in the middle of the prompt, or like it's all the way at the front of the prompt and forgotten. Or so this kind of use cases where you already know what you want to do. Okay. Like for example, in ARC, we already know the program we want to do, like shift the red square to the right, one square to the right. Like I tried using GPT to say shift the red square to the right, like verbally mention that, and then apply it on the test set. It didn't work most of the time. Okay, so there's some issue with GPT following the rules that you said, especially if the rules are a bit ambiguous, like rotate the square. Like it's not very obvious how to do 2D rotation in the ARC challenge. So rule-based approaches should be used. In this case, for the ARC, you should use something like functions. Okay. It does not know how to generate zero-shot functions of what is not commonly occurring in the training set. Okay, this is especially true for ARC as well, because a lot of things don't happen naturally. Like stuff like crop the image, rotate the image, reflect the image, all these kind of things are not really common programs. All right, so they don't really do quite well. You need to kind of give some examples. So this is where the few shot comes in to help to guide generation for ARC. Okay, then next is we have a 1D problem. Okay, the transformer is essentially a one-dimensional kind of method. ARC is a 2D problem. Okay, how do we solve this? Right now, we just convert the 2D ARC into a single line, into a 1D kind of thing for analysis. But in the future, I can imagine that you can use the vision module to help with the representation. Maybe you can use the vision module to describe the image, like, oh, there's a blue square. However, I do think that because the ARC domain is so different from natural images, the vision module may not be able to generate that well. Because I did try Blip 2. Blip is the visual question answering. You give an image and give a question, and the model can give you an answer. I tried Blip version 2, the larger model, and it cannot describe the up data well. All right, it's definitely not trained well on those kind of like synthetic squares like that in the grid. So I'm not too sure whether the 4V is useful for this case. Okay, because yeah, the training distribution of the vision module might be different from up. But definitely, if you train it on up itself with some labels, I can foresee this kind of module to be very helpful with describing the image. Okay, so I have another chat. GPT-4 is actually pretty good at following strict instructions, but not when it comes to actual numbers. Yeah. So strict instructions, yes, if the prompt is short enough. Yeah. If the prompt is long, you'll realize that it soon forgets what the instruction you gave it. There's also the thing about numbers. It's something I'll to highlight as well. Numbers, the vector representation is not native to GPT. Like, you know, if I were to talk about numbers like here, this is like number 1, right? In the number line, the number 1 and the number 2, okay, can you see that the number 2 is actually twice the magnitude of 1 in the number line? Can you all see that? And then if I have a number called number 9, can you see that this number, the magnitude on the number line is actually 9 times that of the vector of 1? Okay, so this is the problem with numbers, you see. Numbers, if you want to represent them in vector representation space, you kind of need to ensure that all these numbers are given like same weightage, like so that when you add, you can add the vectors. When you multiply, you know, it's also an addition kind of thing. So right now, because of next token prediction, I highly doubt that your digits are represented in this way. Okay, so what is likely happening is that they're just using some form of they're just using some form of patterns that that you have seen before in the training data and trying to extrapolate further. So if you have seen all kinds of addition, like all 3-digit addition, all 3-digit multiplication, you've seen all this in your training data, great. Maybe that's what OpenAI use for their training as well. Maybe secretly they have a calculator generating lots of equations and then they fine tune on that. I don't know. I mean, the math inference abilities have improved significantly since they first released. So I'm not sure what they did internally, but I wouldn't be surprised if they actually like just hard coded or just fine tuned directly on the math itself. But this is not the way to go for numbers. Okay, so if you want to do number manipulation, it's best not to use LLM. Okay, so you ask how much arithmetic is there in up? Actually, not really. It's only shapes and stuff. So we don't need the number representation for up. Okay, for up, what happens is that if we actually give the grid in terms of a grid of numbers, like for example, like this, if we give the grid in a grid of numbers like this, 0, 1, 1, where each number represents a color like that. Okay, what happened, okay, in my initial experiments that I did like that, what happened is that GPT did addition, subtraction, modulo to all these numbers, which doesn't make sense because you don't multiply a color, right? You don't add a color and so on. So this led me to change my representation of the problem. Okay, later you will see my representation for this. I changed it to letters like A, B, 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 C, D, because I just want to give it a symbol. Okay, I don't want it to, based on its prior knowledge, infer that it's a arithmetic operation. So I find that using this kind of symbols work much better for up. So I mean, for all of you who want to do up next time, use letters. Okay, don't use numbers. Numbers are not good for up. All right. So yeah, I digress a bit, but yeah, I just want to highlight that transformers don't do numbers very well. So, okay, this is the key inspiration for my methods in the up challenge. So language up. So the key is that most of the original up tasks, like for example, this is the original up task. Here we have move each colored square so that it covers the closest corner of the 2 by 2 light blue square. Okay, can you see that? Like here, shift here, and so on. So this can be unambiguously described like that. And then the builder, just seeing the test case. Okay, this is the test case. Can use this instruction here and apply this instruction to get the answer without even looking at the training cases. Okay, so it's found in the language arc paper that about 88% of tasks can be done in this way. And so this was the inspiration. Can GPT be both the describer and the builder? So this is where my inspiration came from for GPT, because if we can do this, we can effectively maneuver ourselves into a space where it's semantically meaningful, which is this description. And then we can maneuver back to applying this description back to the input domain. So, all right, let's find out whether it's possible. Okay, so I call this the 7 steps to greatness, okay, or 7 steps to solving up. Okay, so these 7 steps were added on because the initial steps didn't work out too well. So I keep adding and adding and adding, and after a few months, this is what converged, all right? And I think this is more or less the correct way already. I'm happy to hear more feedback, okay, because obviously I haven't solved the ARC challenge, but I think I made more progress than a lot of people using GPT on this ARC challenge. Okay, so first, we go to the language arc model, all right? What do we have for the language arc model? We have the training examples, and then we prompt it to a language description like that. After that, what we do is we use this language description and we execute it on the arc test examples. Okay, what's the problem? As you saw earlier, 88% of these language descriptions don't really match. Okay, 88% of the language descriptions don't match with the training examples. Like, I mean, you can really tell there are some cases whereby, you know, you have to replicate a pattern only at the top half, but not the bottom half. But the top half is like only certain shapes that you replicate. Yeah, this is very hard to convey, like especially stuff that has irregular shapes. Like if it's square, rectangle, I think that's fine. But if the shape is like this L with like, I mean, it is very hard to convey in language, in English. Okay, then your language description may not be a good way to kind of tell you what to do for the test examples. Okay, so what I did, okay, instead of just using only the language description, I actually still, when applying it on the test examples, I actually still give the original 2D grids. So this is what is added. So you can see that this escape connection here is actually not that difficult, because what I did was chain of thought prompting. I asked it to like come up with language description, and then after that, use language description to apply it on problem, on tests. So all this, I put skip connection there, is actually a chain of thought process, and then the model itself does both the language description and the examples itself. Okay, but if we were to split into 2 models, my recommendation is to still give the original input grids, because these original input grids do help a lot with solving the problem. Okay, then I faced another problem. Okay, because I tried to do initially. Okay, let me tell you the initial ambition. My initial ambition is that GPT can solve everything. Yeah, I was quite optimistic. Okay, but now I'd like to tell you that GPT cannot solve everything. So that there's more to just blindly using GPT. You need a structure, you need a system. Okay, and that's what this whole paper is about. So this part here has problems. This 0 short execute has problems. Why? Okay, anyone can tell me why do you think this would fail? Like anyone? Why using GPT to just apply the language description on the test examples would fail? Anyone can tell me? Charles said because it has no examples of output. No, yeah, it has the input output examples already. Lack of context. Okay, actually not really lack of context. Okay, maybe let me just share with you why. Okay, the thing is it has the instructions, but it may not be able to execute them properly. Like you say that shift the rate square to the right. Okay, but the thing is, in GPT terms, what is a rate square? A rate square is like, a rate square can be like x, x, b, b, x. I mean, let's say b is the rate square, okay? So if let's say I ask you to shift the rate square like 1 cell to the right, like you see the description of the description, let me just write here, description of language is in a different domain to the grid. Okay, there's a domain mismatch over here. And also another problem is that sometimes you ask it to do like one square to the right, it doesn't really follow through also because there's a reliability issue. Yeah. So Charles said, from our perspective, the task is shifting, but from GPT's perspective, it has to iterate, removing one of the points and adding another point. Yep, that is correct. So the thing is, there's a domain mismatch. We want GPT to shift the red square one cell to the right, but that's not how it is in text. Okay, in text, you need to copy and paste that thing, and then you need to like shift the X. So like in order for this to appear as this, this is not like in order for this to happen, like if you were just to say like shift red square one cell to the right, like what is it? I don't know. Yeah, I mean you can prompt it. So that's where the prompting comes in. So we actually need to prompt it like what are the input and output examples representing, what are the different colors representing, like so shift one cell square red square one cell to the right. You may or may not know it. Okay, so you can try to prompt it more, but the thing is because of this domain mismatch, and also GPT is not very reliable at executing the instructions. Okay, you can try it. As I mentioned earlier, you give it a rule, you ask it to keep applying the rule. Chances are there are some cases where it will fail. We don't want that happening because in ARC, one square wrong means the whole thing is wrong. We want reliability. And that's where we need something more concrete, something like a program. And that's version 3. So we encode it into a program. This program is a Python program. I mean, you can use other programs as well. It doesn't really make a difference. So in this Python program, we ask GPT to come up with a Python program. And then after that, execute the code to apply it on the test examples. Okay, there's another problem now. Okay, I mean, you have thought this is great, right? Oh, what a great workflow. We are done. But that's not it. That's not it. I mean, even with this, it still cannot solve a lot of things. Okay, because, all right, there's a problem with the input. This 2D grid itself, okay, you imagine that just now I say it's a red square. How does the GPT know what's a square? Right? From a chunk of 2D grid, like how does it know what's a square? How does it know where's the position of a certain thing? I mean, to us it might be easy. We can like reference the grid coordinates, but to GPT it's not innate. You see, the grid coordinates are not there. So if you want to do stuff that involves grid coordinates, you kind of need to give the information in the inputs as well. You kind of need to give what is a red square, what's an object. So stuff like this, I find that like imbuing the object view has helped to improve my solve rate by twice. Okay, so object view is very important. GPT doesn't extract out objects innately. I tried to prompt it. I tried to prompt GPT say objects are continuous cells together that are separated by different color. You know, sometimes it got it, sometimes it didn't. GPT-4 is not bad actually. It's just that we cannot accept sometimes can, sometimes cannot. Okay, because in the ARC challenge, one square incorrect means the whole thing is wrong. So yeah, we kind of want some reliability here. And so how do we do this? So let's go for a diversion here, all right? What I want you to see here is the image. Okay, so why am I showing you a dog with a frisbee, right? So I want you to focus on this image, okay? Okay, can anyone tell me what you see in this image? Yeah, you can just type in the chat. Like if I give you this image, what do you see in this image here? Yeah, please. And I wait a while for you all to type it out. Okay, Volodymyr say dog with frisbee on the beach. How about the rest? Okay, so okay, Charles say dog holding frisbee on the beach on sand, blurred background of people. Okay, so you see, everyone has a different kind of focus. So most of y'all said dog with frisbee. Okay, but this image could jolly well be beach with water, right? I mean, the dog may not be the focus of this image. I could be focusing on blurry background and sand. That could be my image. Then the dog is not the focus, right? But right now the dog is the focus, but it need not be. What if I told you that the image is actually characterized by dog with white and brown fur, and brown, white and brown. Yeah. What if I told you that this is the focus of the image? Then this is something that is not really intuitive. You see, like if I just ask you to focus on the overall picture, you will only see one thing. You will see like dog holding frisbee on the beach. If I ask you to focus on the dog itself, maybe you can tell me the dog has brown and white fur. If I ask you to focus even more, you can tell me the dog has eyes, ears, and stuff. So like this becomes more and more like more micro, more like pixel view. You go further, it's object view, and then the most generic view maybe is a grid view. So it appears there's multiple hierarchies when it comes to solving this problem. So we kind of want to do the problem at different levels, and I think this is the highlight of this paper, of this approach. Okay, most approaches I've seen only do one kind of view, like only object or only grid. But why not just combine all different views together, mix and match the views? Some problems you need to focus at the micro level, some problems at the macro level. Why only constrain to one certain kind of view? So what we can do is we can have different agents, okay? The idea is that each agent does different actions, okay? But right now, all my agents do the same action. So this is future work, okay? We will have different actions in the future. So what if we can have different hierarchy like grid, objects, pixel, we have different views, generate programs for each of these views or a combination of these views, generate the Python program, and then we filter it. Okay, can we do that? And let's see what these views are. So for example, grid view, you can see that my black squares are represented by dots. Okay, my red square here is represented by an F. Okay, my yellow square is represented by a D. Okay, I don't know whether this is yellow or green. Okay, maybe it's light green, yeah. And this green square here is represented by a C. So grid view is essentially just taking the grid and converting it into letters. Okay, what's this object view? Object view, there are a few different kinds, like you can have the same color object as one object, or you can have an object with multiple colors. So over here, we have a single color, so the object view becomes like that. So this thing here is this one here. I use a different color. Like that. Yeah, I think you cannot see this color as well. Let me just change the color. Maybe blue color. So this thing here is actually this object here. And then this thing here is this object. And then this thing here is this object. You can see that each object has certain properties. Like, for example, what is the grid it occupies? What's the size? 3 by 1. How many cells it has? What's its shape? Okay, I purposely gave all this, okay, because all this needs to be done, okay, in order for some problems to be solved. Some problems go by shape, some problems go by size, some problems go by cell count. So Charles asks, did your LLM convert the image to grid view, or did you use a Python program to do it? Okay, so initially I tried to use the all large language model method, but it didn't really work too well. Okay, even asking it to convert into this kind of objects, it might fail. Okay, even if you give it some examples. So I've decided to just use a program. Okay, because all these views are fixed. Like grid view, object view, pixel view, all these are fixed. All done using a Python program. So to answer your question, all these are done using a Python program. Yeah. Okay, yeah. So for the next one, we have pixel view. So pixel view is saying like, oh, this color F appears at squares 0, 2, 1, 2, and 2, 2, and so on. Then D appears at this 1, 1, and 2, 1, and C appears at 2, 0. Yep. So you can see that all these views are helpful for solving different kinds of problems. Okay, the grid view is helpful if you need to rotate the grid, you need to duplicate the grid, and so on. Object view is helpful if you need to manipulate each object differently. Then you can just treat this, then you can just treat each of these things here as a separate entity, and you can do some operations on it. The pixel view is very useful if you need to like extend your row, or you need to do some manipulation at the pixel level, like maybe you need to remove the last pixel of each group. Yeah, so maybe you can, or first pixel of each group. You can do that in pixel view, okay, which is very hard to do in maybe object view. So each view has things that is good at manipulating and things that is bad at manipulating. And this is my hypothesis. If you can manipulate things in the right way at different levels, okay, you can solve a variety of problems. Because some problems in life require you to like for example, if I ask you to replicate a painting, okay, you need to know exactly what pixel each position has. So you need to remember everything. Okay, that's pixel view. If your task is like describe the picture, then you can use like object view. A dog have a frisbee. Okay, if let's say your task is maybe to do something with like you need to identify where left side of the picture is and right side of the picture is, maybe you can use grid view. Yeah. So I mean, of course, there's more views like segment view. Like you can have a segment like this particular square that I haven't really programmed all these views out, but I think those kind of views will be useful. So there are different ways to abstract the input domain into something that is more friendly for GPT association to happen. And that is why all these views are used. Okay, and any questions so far on all this? Because this is very important for this the solution for this ARC challenge.
So for example, if
Yeah.
we were to ask LLM to basically design an ARC test of itself and also come up with all these layers of layers, would it be able to derive all these different aspects, or we will need to kind of slice it like you just mentioned, and then just give him specific, like more or less specific task to solve it layer by layer?
Yeah, you're talking about generating your own ARC problems, right?
No, so like I was thinking how to solve this ARC test, right? So in order to solve this ARC test, we would need to slice and dice all these problems into layers. But if ChatGPT knew what ARC test was and how to generate it, wouldn't it be able to understand that there are different layers, and then it would be able to solve task by task?
You mean have a classifier to classify the tasks into different kind of groups, like grid tasks, object tasks?
Yeah, exactly. Yeah.
Yes, correct. So what you described is in the final system that I envision. I haven't built it out yet, but that's a good point. If you can classify the task itself, you can restrict your action space so that you can only focus on what is more viable to solving it. So that's definitely something that needs to be looked into if you want efficiency. Okay, right now what I do is I just try all the agents and see what works. Okay, that's very inefficient, but this is just a starter. Yeah. So yeah, I exceeded the time a bit. Let me just go through this. So next part, okay, we have all this pipeline set up already. We have done the transformation using a Python program to transform it to various views. Okay, and then we do the language prompting, the code description, and so on. But we have a problem now. Okay, the problem is GPT may not know, okay, what are the actions that arise from this language description. Like if you want to get this code out, we need to know like what is shift what does it mean to shift an object to the right? What does it mean to shift an object to the left? Okay, it's very primitive for us because we have seen how the environment works. But if we want to encode this out in a program, it's not easy. This description, all right, the code description needs to be grounded in the real world, which is the arc world. Like how does the arc world object move? How do you know how to move an object to the right? How do you know how to enlarge an object? So this is not natural. I mean, you could have some 2D grid tasks that does rotation and symmetry. Yeah, you could do that. I mean, it's already in the training set for GPT. But in order to ensure that it actually knows what to do in your kind of environment here, in the ARC challenge, it's best if you can ground it in some primitive functions. These primitive functions are functions that describe how that define all possible action spaces possible. And it is not meant to be very specific. It's meant to be very broad. So like a combination of these actions can lead you to do anything. So ideally, it's something like in the real world, you can walk, you can move your left leg, you can move your right leg. So all these are primitive actions. And then a combination of this can be walking or running or jumping. Yeah, but you don't define run, walk, jump because those are too high level. In the whole hierarchy here, I believe that what you're defining is, okay, because I believe intelligence is all in a hierarchy thing. So you actually defining the low level details. Okay, and then at the higher levels, they actually take a combination or a set of the low level ones to act on it. So these primitive functions are really meant to be the low level functions. Okay, and these are defined by, at the moment, me, okay? Because I haven't been able to really get a list of primitive functions from up. You have to, I basically look at the first 50 training set problems and identify what I think the program needs. Okay, so this could be improved, but this action space grounding, very important. Okay, a lot of work in large language model doesn't work in the real world because it lacks the action space grounding. And if you ground it on sufficiently broad enough action space, it will end up to be something like Voyager. Like, you know, Voyager is the Minecraft agent. You ground it in some stuff like A star search, shooting the monsters, and so on. Eventually, can be able to use a combination of these functions to try to solve the world. Like same as the goals in the Minecraft. Yeah. So grounding in action space, very important. So that's what we will do next. We add in some common functions that does the input-output relations. Like for example, flip, okay, horizontal flip, vertical grid, or replace. Okay, then I find that just giving this zero-shot description is not enough because it's not grounded in the world of art. So I just added this assert over here. I mean, I did unit test to test all my functions, and I just copy paste my unit test in, and GPT understands it. So this is the prompt for GPT: the zero-shot description of the function and the one-shot example to ground it in the world of art. Okay, so this worked very well. I mean, it improved my solve rate so much after I did this action function grounding. And I would like to say that most of the tasks are not direct applications of these functions. They require like a combination and so on. So I would say that this is not like hard coding the art. Okay, rather we are just giving mechanisms for LLMs to interact or interface with the world of art. Because LLMs are text-based inherently, we need to bring it into this 2D space. And these functions are very useful. Okay, questions so far on this before I move on? Oh, okay. Because this action grounding is something that is the link bridge between this method and traditional rule-based methods. Okay, you know, traditional rule-based methods like domain-specific language, the DSL methods, where you come up with a list of functions, a whole broad list of functions, and ask a brute force program to choose. Okay, the problem with that kind of approach is that there's too many possibilities. What GPT does is that it filters the possibilities by comparing what is needed, okay, to what are the available functions. So it's in some sense able to help to filter the respective functions. I mean, you can treat it like tool use. You are filtering the tools, okay? You're choosing the right tools to use for your program. So this is actually the same problem. What are the tools to use? Then the next question is, how do you come up with those tools? And the how do you come up with those tools is the problem I haven't solved yet. Okay, but given these tools, okay, if you ground them in the right wording, you ground them in the right examples to the environment, it works wonders. Okay, I'd like to highlight another thing that I found is that grounding in too many tools leads to poorer performance. It's counterintuitive, right? You would always say that, oh, I increase the context length of my LLM, I will get better performance. That's not true. Okay, by my experiments, if I ground it in too many tools, okay, actually the tendency to use irrelevant tools becomes higher. So it ends up using functions that it's not meant to use. Yeah, so these are some stuff that needs to be guarded against. So in the next version of this work, I will constrain the tools to make it like smaller, more concise, so that the agent is able to pick the right kind of functions better. And yeah, I think this is something that I discovered. I think there are some recent papers that talk about it also. If you retrieve too much context for the RAG system, retrieval augmented generation, it actually leads to poorer performance. So this is something that needs to be looked into. But I think for the case of ARC, it just means that we need to have more specialized agents, okay, that can solve the problem. Yeah. Okay, Charles asks, what are some of the considerations when breaking down a complex task into small specialized agents? Do you experience inaccuracies, especially when the result might need to be compiled by a separate LLM? I think the main thing about splitting the task is that the split must make sense. Like for the respective agents, how I split them is currently by the views, like what what level of the hierarchy are you giving the problem. Okay, so if you can split down into this kind of hierarchy, it's very natural to split the agents. Okay, do you experience inaccuracies, especially when the result might need to be compiled by a separate LLM? I think this case, I don't really see the inaccuracy because right now everything is actually, all these agents are actually still one large language model. It's just using chain of thought to prompt. Okay, if you want it to do with a separate LLM, if you just paste the relevant context, I don't see any problems of the inaccuracy. I don't think the inaccuracy will happen. So I think what's more important is, are your primitive functions sufficient to cover the entire space of ARC problems? And this is an open problem. What are primitive functions? I don't know. Yeah, the one of the problems with the ARC domain is it's too broad. There's too many primitive functions you can actually have. Okay, so I haven't covered all the list of primitive functions, but I find that GPT is quite versatile. Even if I don't provide the function, if it's related, right, it can actually kind of, I mean, it doesn't change your function, but it can sort of generate a function that does similar stuff to what you've coded. Yeah, so GPT is quite versatile. It's able to code itself, the primitive function, all by its own if needed for some cases. Okay, so the next thing is primitive functions. If you just want a sequence of functions, I mean, it sounds very, very nice, you know, like process 1, process 2, process 3, process 4. If we just do this functions-based stuff, you know, it may be too lengthy, okay? It may be too lengthy. So what I did was to add an if-else statement kind of thing, if statement here. So we can add conditional code saying that, okay, you can only do the thing if you do an if statement. So that's a if over here. Like, and this if statement helps to ground the generation of the program into a much shorter program. So you can see that this is the DSL program by Michael Hodel on this problem here. So the problem requires you to, if there's a row and a column square match, you connect the squares, like for example, like here. So you don't connect all the squares, you see, you only connect stuff that have in the same row or column. So this is something, if you don't have an if statement, okay, you're going to have a very long program. So if we have an if statement, and then we can come up with some conditions that are commonly occurring, like for example, objects in the same line. Okay, in this case, objects in the same line. There are other if statements also, like object within another object. So if you can come up with this kind of conditions, yeah, this will actually help to reduce the overall length of your code. And reducing the overall length of the code helps with more accurate code. Because if your code is too long, it tends to be incorrect. So conditional code is something I'm exploring. Right now, if you take away the conditional functions, you will have maybe 1 or 2 problems less that are solved. But I don't see these conditional functions really helping much right now in the solution, because I only gave 2 functions, like object contains this color and object on the same line. Okay, so I'm still thinking about what kind of conditional functions are needed. But I do see that there's value in this, because there are a lot of problems that it's like, if your object cell count is more than 6, okay, then change the object color. Yeah, so stuff like that, I didn't encode a conditional function because GPT is able to do it by itself. Yeah, but stuff like if the thing is on the same line, if the object contains a certain color, yeah, I think eventually, if the primitive action functions is if the abstraction space, like the pixel, object, or grid, is detailed enough, I think GPT is able to come out with the if statement by itself. Yeah, this is my sensing, because I realize I don't really need too many conditional functions. Okay, so yeah, this one still needs more experimentation. But one thing is for sure is that conditions help. Okay, it helps a lot actually. So next, we did all these systems already. Everything is great. What's missing? GPT doesn't know that whether the code is executed correctly or not. Okay, in GPT's point of view, all it comes up with is a string of text. Okay, in this case, I did a JSON prompting, so it outputs everything as JSON. So to it, it has outputted a JSON. It doesn't really know that the code needs to be executed. How do we tell what to do for GPT? Like, how do we tell GPT whether the code is done correctly or not? Anyone want to offer some suggestions? How do we let GPT know whether the code is successful? Yeah, maybe you want to just chime in here. Charles said, give it examples of output. Okay. Yeah, Volodymyr said, give expected results. Yes, that's correct. So we give the results of the code, okay, be it compile error or is it inaccurate results or what, we give it back to the program. So this is something like Voyager. You basically do a recursion in terms of like the environment feedback gets put in as the context, okay, for the generation of the program over here. So this work is heavily influenced by Voyager. When the Voyager paper came out, I added this into the system, and it solved quite a bit of problems. So it's not bad. This method works, the grounding in the environment. And so we have this new thing called environment feedback. Oops, sorry. We have this new thing called environment feedback here. And this environment feedback helps it to learn more views. Helps it to improve the program to make it better. So right now, this thing I think this environment feedback is very, very important. So as the action grounding, so as this grid view and everything. All this, you can see a common theme of all this. And the theme is to help GPT understand the data better. And that's the theme. Okay. Okay, so there's one last thing here. Okay, so this system is not solved. There's one last thing. Okay, is that the system is not actively learning the new functions. So how do we solve this? So the idea to solve this is actually in memory. We can bring in memory, and memory, okay, in this case is like this. Okay, let's go through step by step. Okay, so you have this classification head, as what Volodymyr said just now. You can actually help to filter the space of agents that we want to consider. Okay, so right now I haven't implemented this, okay, but if you can have a way to classify the problem into like grid view, object view, and so on, you can target the right agent to solve it. Okay, then we can map it to the right abstraction space, be it grid view, object view, and so on. So this is the grid, object, pixel. Okay, we can also give it like stuff like past examples. Like over here, you can see that this is the program for the memory bank. Okay, so if let's say the program has been solved successfully, maybe you can give it more examples of successful code that has been done in the past. Okay, maybe this part here can just be like description of program plus the code. Okay, then of course, we can also learn new functions. So we can also learn functions from successful solves. So this is very similar to Voyager. You can solve the problem, and then you can use memory to guide the generation again. So this whole thing here, okay, after you classify, you do the chain of thought prompting to generate the program based on some helper functions. Okay, generate the Python code, run it. Okay, do the environment feedback. If compile error, feed it back. Okay, if it doesn't match the training sample, okay, you can also feedback the incorrect output. Okay, but over here, I did something different. I basically say that the output is now the input, and then you do a new input-output relation. So it's like if it's a two-step problem, I find that GPT can actually do the first step pretty well. And then all it needs to do is some nudging to do the second step. And so if it generates this one first, I then make the problem simple. I make the problem become like that, this input-output problem. So yeah, I mean, initially I tried to give the wrong output as the prompt, okay, but the problem is that the context length got too long. Okay, that's why I did this method. This method works pretty well also, so I stuck to it. So this is how I envision the ARC challenge to be solved. We use memory to learn stuff from new problems. Okay, so you can keep learning and learning. We use different abstraction spaces to view the different problems into different hierarchies and solve problems at different levels of hierarchies. Okay, so I'll just pause here for a while. I know it's almost ending it. Maybe I can just end here and I can continue the rest another week. But just based on this initial thing, anyone has anything you want to add on or like clarify or anything?
Yeah, just like about this particular part you just explained. So if you say if we are succeeding in the first step, right, then we just do a nudge to get the second step done, because it already will be much easier for the LLM to figure it out. Is that correct?
Sorry, if you get the first step wrong, then okay, can you repeat that again?
No. You just mentioned that if we get it right, if we get
Okay.
the first step right, then the also wait. Is it better? I think this mic is better. So basically, if we succeed in teaching LLM how to do very well the first step in our sequence, then subsequent steps like step 2, 3, step 4, it will require less guidance, is it?
Yes. So if you succeed in the classification step, you can constrain your action spaces, you can constrain your agent types, and you can basically solve the problem with fewer agents, like
Okay.
fewer different kind of abstraction spaces, because you already know who to. It's like, in a company, if I want to solve problem A, then I can identify who are my workers that can solve it. So if I already can have a good way to identify, okay, worker A and B solve this task very well, I don't have to ask all the workers to generate a solution, right? I can just use worker A and B.
Makes sense. So what about like every next step? If, for example, classification was correct, that's great. So we now have the agents, but also we have some of the parts. It might be that some of the parts are done by LLM as well, right? So it's not all agents, but can be a combination of agents and the LLM itself.
Yes. Right. So this whole system is rule-based plus LLMs. So I combine both rule-based and LLMs because I don't think LLM alone can solve intelligence. It's too versatile. It's not consistent enough.
Okay.
Yeah, but what LLMs can do is it can guide the generation. It can guide, because of the way that it's able to do next token prediction, it can give some semantically meaningful answer. So it's able to know that, okay, this is a problem of the object level, or this is a problem of the pixel level. But it's able to match the functions to the description. So that's something very powerful that LLM can do that rule-based cannot do.
All right, understood.
I have a question on my end.
Okay, yeah.
Yeah, so actually I'd like to know a little bit more about what you mentioned about breaking things into primitive tasks, because you mentioned a lot about how, generally for a problem, you find an increased accuracy as soon as you break it down to smaller parts for the LLM to deal with, right? My question is more of like, do you know if there's, or do you imagine some kind of scoring system for understanding what kind of, level we should be breaking the tasks into to maintain certain levels of accuracy? For example, how would I be able to understand, for the problem that I have at hand, how basic do I need to break it down into its individual components for the LLM to solve before conglomerating it back into one bigger entity? Because obviously I want to aim for accuracy, but I don't know, if it's going to take too much work to break down the thing into like a million different steps, as compared to like maybe 2 or 3 steps.
Okay, so in this case, for the problem that I was talking about, the context length, right? It's not about joining back again. Okay, it's just if you give, let's say, if you give too many of these functions, then sometimes if the problem requires like a horizontal flip, okay, it might actually call in another function X over here, because you gave it that function, it just matches it. So it's something like, in retrieval augmented generation, you give too many documents, sometimes the chance of you getting a wrong document is higher compared to if you filter the documents already, and then in that filtered space, the chance of you getting the match is higher. So in this case, I'm talking about the filtering step. So if you can filter the functions needed, and then you give these functions to GPT, the accuracy is higher. Yeah, you not necessarily need to like conglomerate or match up all the different agents back up together. You don't really need to do that.
I see.
I'm just saying, yeah.
All right, thank you.
Yeah, no problem. Vladimir, you asked what about application of failure probability with every next step? Do you want to elaborate that, or have you asked that question already?
I think I know what he's referring to.
So explain. Thanks.
Okay. Sorry, we're both from the same company, so we've been working on this problem for a little bit. Basically, amplification of failure probability is the phenomenon that was experienced by a meta paper, whereby what happened was that they basically tried to put a bunch of GPTs together to work in a workflow. But what they experienced was that because they only gave each GPT a fixed input-output format, as soon as one GPT in a chain kind of like went out of line or gave an unexpected result, the failure compounded by a lot. And they noticed that the end result or the inaccuracy at the last like step was much higher if they had like 10 agents as compared to if they had like 3. So I mean, we're thinking about this from your context.
That's understandable. So it's like, let's say if I do the classification wrongly at the start, I will expect my next few part to be wrong as well. Because like if you get the wrong agents to do the task, it's unlikely you get the right answer. So in this case, the failure is very, very high if we do this classification module. That's why I haven't done this module yet. But I had to manually, run all the agents, which is very time consuming. So I think this idea of application of failure is real, okay? Because if you were to do process-based systems, any part of the process fails, it will carry over to the next part. And so there needs to be ways to error check or fact check and make sure that each part of the chain is robust. So over here, the fact checking is actually done using, okay, in this case, you can treat this whole thing as one workflow. Is done here. If it matches the training samples, it means that the process is correct. So what I do is I do a massive generation. Everyone generates programs. Then there's this gate to filter it. So you can call it the truth gate. Okay, it doesn't matter what your earlier processes do. As long as it doesn't pass this test, your program is not a good one. So at least when we go over to the next part of the program, which is like over here, the error doesn't carry forward because there's a gate here to measure whether or not it's done properly. So of course, in the process, you can help to give some guidance. You can say like, oh, I'm going to give you some helper functions to make you generate better and so on. But essentially, you will need to have some check. If you don't have a check, I mean, the check can also be LLM-based check. I mean, surprisingly, if you ask the LLM to check itself, it can improve performance because it can catch errors that it otherwise wouldn't have if you just generate like that. So if you have some forms of checks, I think this would help.
Okay.
I mean, I don't know about your use case, but at least for the case of ARC, the check is whether it passed the training set.
Yeah, I think we can figure out the rest, but very good ideas. Thank you.
Yeah, so I think I won't really have time to cover the rest, but let me just share roughly what are the results, okay? So that it solves about 45%, which is like 111 out of 400 training set problems. Okay, I'm just going to spend about 5 minutes covering the rest of the slides, all right? So there are different views. Okay, grid view is used by default. Object views, there's different kinds, like either you consider all colors together or only one color. Do we constrain the objects by row, column, same color, or do we want diagonals to be part of the same object? So all this. So in pixel view also we have two kinds, on or off, like basically whether or not to put coordinates into the view itself. So we have 3 tries for the agent, up to 3 environment feedback loops. Okay. So over here, I'd like to give a caveat, okay? For problems, sometimes I didn't try all the agents, okay? Because if one agent succeeds, I just stop there, okay? Because there's no need to have a second solution that works. Okay, so this is and for some other problems that I know that GPT is probably not able to solve it, I didn't try all the agents either. So this, sorry, I saw 50 out of 100. This is okay, let me just put here, 50 out of 100 is the minimum possible. Okay, because I didn't really brute force everything out. Okay, I tried my best, but it's a lot of agents to try. So I think it's actually higher. Yeah. Because if you were really to try out all the agents, I think you can even hit a higher number. Okay. So 45% solved. Okay, I'd like to highlight the use of environment feedback. We have 7 cases solved with iterative feedback. Okay, 6 incorrect output, 1 compile error. So the environment feedback is very useful. You can see that in all the views here, the object view is the one that's actually used the most. That's quite impressive. Okay, there's also 61 out of 111 tasks not solved. Okay, 3 of them are partially solved. okay, which pass the training but not tests. Okay, this is because in the test they come with something very different. Okay, so I don't really blame the agents for that. Okay, there's also 8 tasks with correct description but wrong program output. Okay, which highlights that the language part may be good, okay, but the program itself cannot live up to expressing that language. So we might need more primitive functions. So just some of the tasks that it has solved. Okay, just give you an example of how the workflow is. So if you look at this kind of task, you have the number of objects here as the number of squares in the diagonal. It looks easy, right? But actually it's very difficult to code this out because like you need to know that it's an object count and then you need to match it to the diagonal. So this is how GPT was prompted using chain of thought. So I used my framework called the strict JSON format. So I have this repository called the strict JSON where you have to pass the LLM output into JSON. So using this format, I got the fields out, like ask you to reflect on the answer. Okay, so this is, if you have environment feedback, it can help to like, okay, why is the code wrong? Why is the output wrong? Okay, what are the pixel changes? Okay, what are the object changes? Okay, what are the helper functions to use? And then what's the pattern? Okay. And then after that, plan out like step by step how the function should be. Okay, I find this step useful also because if you give step by step 1, 2, 3, this Python program will follow this program instructions and get a much better program. So you can see this chain of thought happening at a lot of layers. Like I iteratively ask it to think like think in the domain of pixel, think in the domain of object, think in the domain of helper functions, and then finally find out the pattern. So this is basically a way of doing broad to specific generation that I find that it has helped. And eventually the output of all this will be a Python program. So just to show you how this is done for that problem. So that problem is like, oh, the object in task involves objects found in the grid, okay, reduced to single cell in the output grid, okay, located in a diagonal line. So actually the reflection itself is more or less already correct. So you can see that pixel changes, they say that the number of pixel color H decreases. So actually pixel change is not the main thing, but the pixel change have this diagonal line from top left to bottom right, which is useful. Okay, because in this case, the first domain, the input is in the object domain, and the output is in the pixel domain. Okay, so it helps to have both views. Okay, the object changes is that the object remains the same from input to output, number of objects. Okay, each object is simplified to a single pixel. So you can see that in this case, the object view is enough for the whole problem because you can just say that each object becomes a pixel, and it's exactly what we need to do. So what we need is we need to get the objects, okay, we need to get the empty grid and so on, and fill the grid. So GPT is doing very well for this. And because my grid is in letters, okay, there's no training set leakage because the JSON that's online right now is all in numbers. Okay, so if you can solve like this using letters, it means that it really understood how to solve it. And it can even create a program out. So this is something that is not a training set leak anymore. Okay, GPT can really do this. Okay, the overall pattern is now input grid containing number of objects, simplify each object to single cell. Okay, and then you size the output grid determined by number of objects. So very nice. So you can see the program is like use get objects to retrieve all objects, create empty grid, and loop through each object created. Okay, and then this is the program. The program is get all the objects, create an empty grid, enumerate over all objects, and then you fill the value from the top left to the bottom right diagonal with an object. And it's very nice. I mean, like I'm really quite impressed with GPT for being able to do all this because Arc Challenge is not an easy one. And for GPT to come up with this program is really quite impressive. I mean, granted, I have to do a lot of tweaks and tricks, but I think in the future to achieve intelligence, GPT with a system, some rule-based stuff, multiple tools, I think this is a very, very viable path to general intelligence. So these are some of the solves. Okay, if you all don't mind, just give me about 5 to 10 minutes to conclude this. Yeah, so these are the kind of solves for pixels. So pixels are great for problems that need pixel coordinates like this. Over here, we have the same number of colors, same number of cells for each pixel, and then we just want to change it into this straight line. Same thing for this, you just need to extend this over here. See, it's very hard to create a primitive function for all this. It's really difficult. But using GPT is able to like create the relation itself. So you just use a for loop to do all this. So Initially, I was trying to experiment whether or not, like, if I can just code out some primitive functions and let GPT use, can it solve the ARC challenge? I realized it restricts GPT too much. So probably a free flow Python program is still needed because of the way the ARC challenge is so dynamic, so many rules that are possible. It's very hard to encode all in primitive functions. Okay, object view solves. What are the solves? They are usually it's like objects like that, like change this object to this. Okay, rank the objects by cell size and color it based on the number of cell size. So it's able to do the comparison natively. So great. I mean, probably the training set there's comparison operation done as well. Okay, so object and pixel view solves is like if you need to do it like in terms of like extract a certain column and you need a certain pixel for that column, like for example the middle column, then using both object and pixel view helps. So grid view is when you need to rotate the grid like that, like this is 90 degrees clockwise. Okay, sorry, 90 degrees anti-clockwise. And then over here, you just need to duplicate the pattern, like here, reflect here, and then reflect here. It's not an easy operation, by the way. This reflection thing is actually quite difficult, but grid view solves it. So I'm quite impressed with this. Sorry. So what does iterative feedback solve? Iterative feedback solve like stuff that needs like two or more steps to solve. Like for example, the first time GPT did it did everything in purple. But the thing is, we kind of need this square to be gone. But if we feed this as input, ask it to come out with this, it's a simpler problem. GPT is able to know that, okay, I need to remove that square. So iterative feedback helps in that case. Same thing for here. Like the GPT output is like that. It knows that from this to this, like I need to reduce one row, but it somehow forgot about the blue square. So if I give this as input and go here, it's able to replicate out the blue square at the bottom. So this means that currently GPT, let me highlight this, okay, this is a very important point. GPT is only good for like single step solves, or I mean at most two. Okay, any more, you probably need something like a tree of thoughts or something like you need to do some form of tree search. Okay, if not, GPT is very hard for it to come up with a sequence of moves directly at the beginning, especially when it has no like history in it. Like I believe if you have memory, you may be able to plan further. So this is something that is quite exciting, how to imbue memory into this system. Right, so train test pass, but test set fail. You can see that over here, we have all these lines here. And you can see that this gray square here is at the center. But you see in the test output, this is a classic case of, in the module, they teach you something easy, but in the test, they give you something hard. Like in the inputs, there's all just one single line. Suddenly the test output, they give you two lines. Yeah, so unfortunately, GPT only does it for the bottom line, but it forgot that, you need to give the gray square for the top line as well. So, I mean, I would say that in cases like this, it's just a training and test mismatch. So probably I would still count this as right for GPT, because if we were to give it something similar in the training domain, it would probably still solve it.
So what you're saying is that if, for example, we had a training input-output, which would include multiple lines, in this case, 2 lines, it would be okay.
Yes.
I see.
I mean, it's not very fair to GPT, right? Because like, if you ask it to only do one single line, the code is just for one line. Then in the test, you shouldn't be asking it 2 lines. Yeah. And some of these colors are all different, so it's very difficult for GPT because it needs to abstract this thing to be color independent. Yeah. So for my program,
it figured that part out, right? That part he did figure out.
Because when I give it like, for example, object view, I have this thing called object shape. So this shape is color agnostic. Yeah. So it's able to. So if you give it attributes like that are able to be matched from input to output, like it knows that, oh, it's the shape that matters, not the color, then it can solve the problem. Yeah, so what it cannot solve? Okay, it cannot solve stuff that is like very, very tough, like sorting the stuff and ordering them in a certain way. Yeah, I mean, it ordered in some way, but I couldn't get it to flip it. The flipping part was difficult. So it's because of these 3 blank spaces here. Yeah, so so if let's say there weren't blank spaces here, actually, I think you would have solved it. Yeah, same for here. Like to get this specific pattern here, it's very hard to code it out. Yeah. So we also have stuff like, this is where I say the segment view might help. You have this thing here. In order to like replicate it twice here, is somehow proving very difficult for the object view that I coded, because the object view that I coded is like continuous cells. So to the object view, this whole thing is one object. Yeah, so in order to solve this, maybe there needs to be a way to like, from this object, you see whether you can copy and paste into the other cell and you can match. Yeah, like this kind of matching thing is not intuitive for the views right now. Yeah, same thing for this one. It's able to get all the objects, but it's not able to arrange it in the right order. So this is actually quite a difficult problem. I would say that this problem is hard, okay, because you need to know the aspects of all this and put them in the right sections. Okay, this is a little unfair for ARC actually. Okay, if we look at the training input to output, anyone can tell me what's the relation between input to output? Okay, it's very hard to tell with one, but the idea is you take this square here, and then you superimpose on this square. Okay, so you will get this. Okay, and then you take the knot of this, and then you get this. So it's this operation is called a NOR. I think it's a NOR operation. Yeah, so in ARC, there's stuff like logic gates, NOR, NAND, XOR. Yeah, it's not very intuitive for humans actually. I gave this to my friend, and then my friend was like, "What's this?" So I think this aspect of problems I don't really intend to solve, because I don't think this is reflective of how the human mind works. Yeah, so yeah, anyway, GPT didn't solve it that well also, because I don't have a primitive function for NAND and NOR and so on. Yeah, so yeah, another thing is when the background is different, like background is not white, not black, right? Okay, it's not able to extract out the object properly. So this is also one of the issues that I'm currently facing. So there are some things that need to be sorted out, but I think overall, having this abstraction views is a very promising first step to solving the ARC challenge. Some ideas I have is to constrain the functions more by agent type. Also make the output based on agent type. Like for example, if the agent is objects, I don't need to copy and paste into the grid. I can just ask the agent to output a list of objects. Or if the agent is a pixel type, I can ask it to output list of pixels. Keep the problem simple for the agent, okay? Because if they want to bring back to the grid, it's extra work for them. Okay, then there could be extra views that could be done, a better object view, edge detection view, and so on, rotation view, diagonal view, difference view. Now, I'm not going to go through all this in detail, but the idea is more views can actually help. And yeah, finally, the last slide is like, these are the questions to ponder that I have for today's session. The first one is Python code the best way to encode the program? And I mean, my answer is probably not, okay, because Python is too open-ended. Okay? I mean, if you can have a sequence of functions that can be executed conditionally, that's the best. Okay, this is something like Minecraft. Okay, if you look at goals in the Minecraft, I was very excited with this idea. I tried to code it out in ARC. Unfortunately, it's very hard to express everything as a function in ARC. It's too open-ended. The functions need to be learned, as it need to be composed on the fly. Yeah. Yeah, so if you can, yeah, that's right. If you can actually get the thing in a more abstracted view, like the functions, express everything in functions, yeah, you can actually get it out better in a sequence of functions, like what I did for the 2D grid world. Yeah. Isa asks, have you tried Scallop? Scallop is not the food, right? I suppose it's a kind of program, right? I probably haven't tried it before. So what does Scallop do? Is it also a kind of like functional interface? Okay, while waiting for answer, maybe let me just go through the next few questions. So how can we reduce the context length of the prompts? Okay, so one way to do it is to reduce number of functions. Okay, that's a very surefire way. And in fact, reducing number of functions also help with better usage of functions, more accurate usage. So it's not bad for this. Okay, then I mean the other way, of course, is to split into multiple agents and then like summarize the earlier parts. Yeah, I'm not a fan of this method because if we do this, you know, you might lose some information based on the summarization. So I'm keen not to explore this route. I'm keen to just reduce the functions to expand more problems to solve. Okay. So Isa said Scallop is neuro-symbolic programming language. Yeah, I haven't really tried Scallop yet. But yeah, I guess neuro-symbolic would be useful. Like if you can ground this like up challenge in some neuro-symbolic way as well. Yeah, that can be looked into. I mean, as of now, I think the method that I have can be considered neuro-symbolic because it is rule-based plus LLMs. So I would like to say that it's a neuro-symbolic as well. All right, so the next thing is memory. Okay, if you have seen all my earlier YouTube videos, you will find that I'm a big fan of memory. Okay, it's because I find that memory is a way to learn fast. If you just use stuff like deep learning, weights learning, it takes very long to learn the weights because you need to go through multiple epochs. You need to train the model for multiple epochs before you can actually learn it. Memory is like zero shot. I mean, not zero shot, like one time. You learn it one time, you can reference that memory and you will not repeat the same mistake again. So if you can learn the functions on the go and store them in memory, and then maybe use some retrieval or method generation to retrieve the right functions out for that problem, you know, that can be actually very useful. Okay, you can actually do this, like you can learn from simple problems to solve more complicated ones. I think once we settle this part of memory to solve this using ARC challenge with memory, is more or less the holy grail of ARC, because ARC, a lot of times what you do is you build on like the kind of concepts you learn in the earlier problems to the later problems. Like the training set stuff, you can combine what you learn there to solve the validation set and so on. Yeah, so I think this is something that's lacking in the current system I created, and this is something that can be done. I'm quite excited about this. Memory is my core area of research right now. If you look at my other videos as well, I'm learning fast and slow. It's all about imbuing memory to solve things in a goal-directed way, and it solves changing environments faster than reinforcement learning. So that's my landmark idea. You can check it out, learning fast and slow. This GPT as a system thing for ARC, if you imbue it with memory, I'm very sure it will learn much faster. The only problem is how do we like encode this in the context length, because the more stuff you do retrieval for, the longer context length. So that's something that needs to be looked into. The other thing that needs to be looked into is how do you know the function? Like if you don't even know how to get the function out, there's no point, right? Like if you don't know the model answer, even if you can combine the stuff that you learned earlier, it doesn't make a difference because you haven't learned what you learned, what you needed earlier. So this is a huge problem for GPT because not all the functions can be learned easily for ARC challenge. Like stuff like extend the line and then go through the L function, you know, that those are not like innate functions to GPT. You know, those are stuff that may or may not be learned. Okay, and if you don't learn it, you may not carry over the performance over to the next one. Yeah, there's also this other thing. Now I was talking to Rolf Meissner, one of the directors at the Lab 42, and he was saying that there's also an issue with this memory part. Okay? The thing is, a lot of the ARC challenges, they are created such that they don't repeat. So it might be the case that the memory that you have or earlier problems, okay, may not really help to solve the later ones. So specifically for the ARC challenge, maybe memory may not help that much, but I suspect it will still help. But for real life cases, memory will likely help you again because you are likely to experience the same thing again and again, especially if you live a life by a certain routine. Okay, so this is something very, very interesting for learning agents, memory. Arc-wise, I'm not too sure whether it will help that much, but it would help to a certain extent. Okay, last question. What other views or functions are helpful? I mean, I gave some examples earlier, like you can better detect object ages and so on. Can GPT-4V help? Maybe. I mean, if it's grounded in the Arc domain. Okay, so as I said, memory of relations in abstraction should help. Memory of relations in abstraction. Okay, could you explain this part? I'm not too sure what you mean by that. Yeah. So Isa told me that memory of relations in abstraction should help, but I'm not too sure what this means. Yeah,
maybe
sorry.
she means these layers, you know, like what you explained, if you can classify, and this is kind of different layers of what you're trying to solve, but let her clarify.
I do think memories at different layers of abstractions would help. I've been harping this point also, like I don't think memory is just at the text level. There could be memory at different levels of the processing of the hierarchy. So yes, if you are referring to memory at different levels of the hierarchy, yes, it would help. But unfortunately, right now, we don't really have access to the GPT-4 model, and you cannot like ask it to refer to memory at all the different layers of the self-attention. Although I do think that if you can do that, it might be actually helpful. Yeah, if not, actually, I've come to the end for today's presentation. Sorry, I overshot a bit. I hope it was interesting for everyone. I'm still working on this Arc challenge. This is not solved yet, by the way. But I do think that the current system that I have about the abstraction spaces, let me just go back to this diagram. This abstraction spaces, using memory, using chain of thought prompting, using environment feedback, I think all these are very likely on the path to solving Arc. Okay, because I did make quite decent progress on Arc using this whole systems model. Yeah, and it wasn't easy to implement it, by the way. I mean, it took quite a bit of effort, but I think this was worth it. Okay, it showed that this agents architecture can actually help to solve Arc. Okay, cool. Yeah, if not, that's the end of the session. Thanks everyone for coming, and see ya.
Thank you very much.